Okay, guys, welcome back. Today we're going to be looking at proof by mathematical induction. You can see here, proof by mathematical induction. This is going to be chapter 3b. If you look at the syllabus, really all we need in terms of our proofs is just proof by induction. So we just have to be able to do mathematical induction. If you look at specifically what we need to do, we need to be able to prove results for sums and also prove results. If we look at what the syllabus says, we need to be able to prove results for sums using mathematical induction and prove results or prove divisibility results for any positive integer using mathematical induction as well. Today's video is going to be looking at proof using partial sums. I'll make a second video for just full or normal sums, and then I'll make a third video for divisibility. Partial sums and sums kind of come under the same sort of bubble. So example 6, I have to prove using mathematical induction that, and I'm given what we call a partial sum. The reason it's called a partial sum is because it's not written with our sigma notation, which might have something like, n equals 1 to, infinity or something like that written on my summation. This is just a partial sum for n is a natural number. Just as a little bit of a refresher on our set notation, natural numbers actually doesn't include 0. So n can't equal 0 in this particular sum, but it can equal 1, 2, 3, 4, etc., etc. It's also going to include positive numbers as well. So we want to make an initial statement that is going to be to test for n equals 1. N equals 1 being the first term. There's a few different ways to go about solving this. In this case, my first term is 1 over 1 times 2. So I can establish that my left-hand side for my first term is equal to 1 over 2. And my right-hand side when n equals 1 is 1 over 1 plus 1, which also equals 1 over 2, which equals my left-hand side. So therefore, my test for n equals 1 has been true. So because it's been true for my first step, I'm now going to make my assumption. This is called the inductive step. I'm going to make my assumption. I'm going to assume true for n equals k. So I'm going to test for n equals 1. If that's true, I can now assume true for n equals k. I'm now going to write out my partial sum. That's going to be 1 over 2 plus 1 over 6, or 1 over 2 times 3, plus 1 over, if n equals k, it's going to be k outside of k plus 1 is going to be equal to k over k plus 1. So tested true for n equals 1, assumed true for n equals k. Now I'm required to prove for n equals k plus 1. Just in terms of some terminology, this process where I assume true for n equals k, then I prove true for n equals k plus 1, we call this the inductive step. And we call this here my initial statement. If I come back up here to my syllabus, it specifically mentions that we understand the nature of the proof, including my initial statement and my inductive step. My inductive step is my assumption and my required to prove part. My initial statement is my test. So because I'm required to prove for n equals k plus 1, I'm now going to rewrite out my partial sum, and I'm going to include n equals k plus 1. In other words, I'm going to take my original sum here, I'm going to keep this part here exactly the same, and then I'm going to add a k plus 1 term on the end. I'm going to add an extra term, which is k plus 1. So same thing, 1 over 2 plus 1 over 6 plus 1 over k plus 1. This is my kth term, or my k term. Now I'm going to do one more term. I'm going to do k plus 1. So I'm going to do one more term along my iteration, which is going to become 1 over k plus 1, k plus 1 plus 1, which hopefully you guys can see what that's just going to become k plus 2, k plus 2 like so. That is all going to be equal to k plus 1 over k plus 1 plus 1, which again is going to be k plus 2. Now I'm going to split up, like I do with all my proofs, into a left-hand side and see if I can match that to the right-hand side of my proof. So for my left-hand side, hopefully this is going to jog our memories a little bit, because this is going to be true every single time we do this proof. We're going to get this relationship here. Because I've established k terms, and I've said k terms equals k plus 1. When I establish k plus 1 terms, and I include all my terms up to k, but what ends up happening in almost all situations is I can substitute these two terms for each other. In other words, k terms is equal to k divided by k plus 1. So I can put k plus 1 in place of my big summation line here and get k divided by k plus 1 plus my k plus 1th term, which is 1 over k plus 1, k plus 2. That is what my left-hand side is going to equal. Now, if I try to do some algebra manipulation to this equation here, when I have split fractions, normally a good step is to make them all over the same denominator. You can see here is k plus 1, so I can simply just multiply top and bottom by k plus 2 times the top by k plus 2. Then I can put everything over the same denominator. So if I go ahead and do that, my left-hand side is going to equal k outside of k plus 2 plus 1 from my other fraction over k plus 1, k plus 2. Now I'm going to expand out my top line. That's going to give k squared plus 2 lots of k plus 1 divided by k plus 1, k plus 2. If I factorize the top, that's going to give k plus 1, k plus 1 divided by k plus 1, k plus 2. Well, k plus 1 divided by k plus 1 is going to simplify out to just give the number 1. So I'm left with k plus 1 over k plus 2, which if I look back to my RTP step, that is in fact my right-hand side over here. So because this is my right-hand side, that means that equals RHS. And now I write my QED, which means therefore it was demonstrated or something similar to that. So that's my initial statement. So I've done my initial statement. I've done my inductive step. I proved my inductive step being true. So now I need to make my final step, which is my explanation part. So therefore, shown true for n equals 1, assume true for n equals k, and prove true for n equals k plus 1 by mathematical induction.